Hi everyone. In this Connect with Networking video, we're going to discuss Chapter 2, the application layer of the network stack. Let's go ahead and get started. In the internet model, which we will be studying throughout this semester, the top layer, or the layer that is closest to the human being who's operating a client, is the application layer. And so this is going to be the layer that students have the most personal familiarity with because you use it every time you're using an application that connects to the internet, like your web browser or an email client. The application layer is the network layer that is responsible for allowing your applications to communicate on a network. So it's the software behind the scenes that lets things like your browser or your email client actually communicate with other devices on the internet. In terms of how we structure the application architecture, it depends a little bit on what kind of network structure we want to design. There are 4 primary components that the application layer is responsible for: how we present information to the user, how we perform application logic, how we access data that informs our application logic, which we are then presenting to the user, and where we're going to store the information. The oldest version of our application layer architecture is a host-based architecture, and this is where almost everything happens on the server. Back in the early 60s, when we first introduced mainframes with terminals that were connected to those mainframes, everything happened on the server, the large computer that was far away from the user, and the only thing that really happened on the client was input and output. They could see things on their screen, and they could type things with their keyboard that would then be sent to the server. So one device was responsible for the presentation logic, the application logic, the data access logic, and the data storage, not just for an individual, but for all of the individuals that were using that particular device. The advantage of a host-based architecture is that it is very simple. There's only one place where everything is happening, and because of that single point of control, security is fairly simple. Managing updates and software changes is fairly simple. The devices that are close to the user are very simple and usually very inexpensive. And so this actually does have a lot of potential advantages. But the disadvantage is because everything is happening on one device, if that device gets overwhelmed with requests and is too busy processing somebody else's work, your work will see a significant slowdown. And also, because everything is happening on one device, that device has to be very sophisticated and as a consequence is usually very expensive. So while this does have some simplicity, it also has some significant drawbacks. And we have moved away from host-based architecture because of these issues. An alternative to a host-based architecture is a client-based architecture. And this became popular in the 80s, where we moved almost everything that we could away from the central server and did all of the work on the individual client. This was the introduction of the PC, the personal computer. And you can see in the diagram that what we try to do in this case is move the logic for presentation and application and data access onto the client itself. And really the only thing that the server does is provide common data storage. A client-based architecture results in overall hardware and application costs being less expensive. The individual PC doesn't have to be that much more expensive than the simple terminals we saw in the host-based architecture, but the server itself can also be much less sophisticated and expensive. The architecture is also relatively simple, but the downside to a client-based architecture is because everything is happening on the client, all of the processing, all of the data access, that means you have to move a lot of data from the server to the client. If you want to manipulate a database in this model, you need to move the entire database from the server onto the client, then manipulate the entire database, and then send the entire edited database back to the server for someone else to manipulate. And this gets to be very cumbersome and take up a lot of networking bandwidth. So not ideal for work situations where you are trying to share information and manipulate the same information with lots of other individuals. The newest solution, and probably the best solution, which you may have guessed, is a hybrid between the two extreme examples that we saw earlier. Instead of a pure server-side architecture or a pure client-side architecture, modern networks pursue a client-server architecture, where some of the responsibilities are on the server and some of the responsibilities are on the client. And in modern networks, the responsibilities that are assigned to the client and the server vary, sometimes from business to business, sometimes even from application to application. So it's entirely possible that the only responsibilities you have on your client are how you present the information, and everything else happens on the server. A good example of this would be some sort of cloud-based gaming system where the provider does all of the work, does all the processing, actually generates the graphics for you, and the only thing that happens on your client is that you serve up those graphics on the screen for whoever's playing the game. This has some temptations in terms of having very powerful servers that can handle all of the workload and having very simple clients for your users. But like we know from a host-based architecture, this does potentially provide some bottleneck worries. So perhaps in other situations, you decide that you have the presentation logic and the application logic on the client and only have the data access logic and the data storage on the server. In this case, the client is responsible for some of the processing, the application logic. The server is responsible for deciding what data to actually send to the client. So there is a little bit of pre-processing that's happening on the server. And by sharing the workload across these two separate systems, you get a balanced effect. And this is really effective for things like perhaps using an application that is web-based, like Google Docs or Google Sheets. Some of the work's being done remote, and some of the work is being done locally. One more alternative would be to give as much responsibility as possible to both the server and the client. So some of the application logic happens on the client, but also some of the application logic happens on the server. If the server can't quite figure out how to process things, it will send the workload over to the client to finish. If the client isn't powerful enough to process certain things, it'll let the server do the work. This is a very interesting way of designing a client-server architecture so that you have as much flexibility as possible. Of course, a downside to that much flexibility is this is a complex system. So programming an environment that would work like this can be very difficult. When we talk about client-server architectures, an architecture that has most of the responsibilities on the server is typically called a thin client architecture, where the client doesn't have many responsibilities. When you are browsing the web, your computer is acting like a thin client. You might have the fanciest computer on the block, but its responsibilities when it's browsing the web are very limited. Most of the processing is happening on a server far away, and so your client is acting like a thin client. If you are operating a network where the responsibilities reside on the client and the server, or primarily on the client, we would call that a thick client architecture, where you absolutely have to have some serious hardware at the client's location to do some of the processing. The advantages of this hybrid model should be obvious. They are much more efficient because we're distributing the processing responsibilities. They allow different hardware and software from different vendors to work together, and they require less overall bandwidth than something like a client-based architecture. But the downside is because you have so much flexibility, you have increased complexity. Figuring out how to get different hardware and software from different vendors working together is challenging, and in some cases it will require an additional software step, which is called middleware. Middleware is software that has been designed to act as an intermediary or a translator. It sits between an application that was designed for a server and an application that was designed for a client, and it makes the translation from those different vendors and different systems. In many cases, the middleware is completely transparent to the user. It is entirely possible that there is middleware between your computer and a server that is providing its data that you are not aware of. Middleware is a business model in and of itself, and there are lots of different businesses that pursue middleware to make the transition from one application to another seamless for the user, and the best ones you don't even know about. With client-server architectures, there are a few subtypes of architecture that we can pursue. The oldest and simplest is the two-tier architecture, where you only have the client and a single server, and you're distributing the responsibilities between those two devices. In more sophisticated client-server architectures, we add an additional layer. You can see in this picture that the client is only responsible for presentation logic. There's a server that's responsible for application logic, and there's a different server that's responsible for data access and data storage. The advantages of a 3-tier architecture like the one that is displayed here is that each piece of hardware can be finely tuned for its responsibilities. A client that only has presentation logic as responsibilities could have a fantastic graphics system, but doesn't necessarily need much in the way of processing or storage. An application server probably needs a very fancy CPU to do mathematical calculations and number crunching, but probably doesn't need much in the way of graphics and may not need much in the way of storage. A database server needs lots and lots of storage that operates very quickly and software that allows it to access that data for either storage or retrieval, but it doesn't necessarily need fancy processing to do number crunching, and it doesn't need anything in the way of presentation. So we can specialize each of these different devices for their particular responsibilities. We can also scale a little bit easier. If we notice that our network's not working particularly well, we can try to pay attention to what's not working. If it's taking too long to get the data, we need to enhance our database server. If we get the data fast enough, but crunching the numbers is taking too long, we need to enhance our application server. And if it's just the graphics aren't working quite right, we need to enhance our client. We can take client-server architecture to the extreme and add additional layers above and beyond 3. This is a 4-layer architecture, or an N-tier architecture, where we have a specific server for our web services. Behind the web server, we have another application server that does additional application logic. And behind the application server, we have a database server, which is responsible for storing and providing data for this system. Each one of these devices highly specialized for its individual tasks. Tiered client-server architectures have the advantage of being good at load balancing, giving the responsibility to specific devices tailored for those responsibilities, and tend to be more scalable. We add more oomph wherever we need it. The downside, of course, is that each tier increases the network load. We have to move information back and forth from tier to tier to tier, and that does take up bandwidth. It's also more complex to develop applications that take full advantage of these architectures, so there is potentially a development cost. An alternative to the client-server architecture that is still popular today in lots of different arenas is peer-to-peer architecture. The oldest versions of this architecture that many of you are perhaps familiar with are things like Napster or BitTorrent. And the idea behind peer-to-peer is that every device that's on the network acts as both a client and a server. Every device is responsible for presentation, application, data access, and data storage. In the simplest version of a peer-to-peer network, there is one central server, but its responsibilities are not data storage. Its responsibilities are just getting the various clients, which are also the servers, connected to one another. Think of it sort of like a phone book, where you use this central server to look up other devices that are part of this network and also determine what types of files they have stored on those local devices. When a device joins a peer-to-peer network, it's usually to request a file that's stored on that peer-to-peer network. When that individual client requests a file, it will contact that central server, which will look at all the active peers on the network and determine where that file is located. It's entirely possible, in fact, probably likely, that that file is located in multiple places, which means that different parts or segments of that file can be delivered from different servers, different peers, to the peer that's requesting the software. Every device that's connected to this network, every peer, can act as a server delivering content that it has locally stored. The moment that a client requests a file and receives some portion of it, it can start to act as a server as well and deliver whatever portion it has, whether it's part of a file or the complete file, to other clients that might also be looking for the same information. So the moment a peer receives information from the peer-to-peer network, it starts acting as both a client and a server, receiving information from other peers, and sending information to other peers. Everyone cooperates. The advantage of a central server peer-to-peer network is that the central server can act as protection, where it might not store local files, but it could check the integrity of the files that are being stored on all of the various peers. The downside is the directory server can act as a bottleneck. If there are too many people connecting and asking for where certain files are located, that server can be slowed down or overwhelmed. So there has been an alternative for the centralized server peer-to-peer network that's been developed. It's called pure peer-to-peer. There is no central directory or server. In order to participate in a pure peer-to-peer network, you need to be aware of at least one other client that is a peer on a peer-to-peer network. Once you connect to that client, you can then ask all of the other clients that are connected to it, and those clients can ask all the other peers that are connected to them, and your request can kind of percolate dynamically through the system to try to find active file names. This means that the directory is distributed just like the files that are on the network. So the directory is constantly being tweaked and adjusted and distributed amongst all of the peers. There's no central server that's responsible for connections and responsible for indexing the various files that are located on the network. This is pure peer-to-peer. The advantage of the peer-to-peer architecture is that it is very resilient to failure. Because the data is distributed across multiple peers on the network, if a single peer drops off the network, the data is still available from other sources. It also distributes bandwidth requirements, so no individual server or business is responsible for delivering all of the content. That responsibility is distributed across the participants. Downside is that it might be difficult to find stored data, especially in pure peer-to-peer networks where the index is distributed across the various clients. And there may be a security concern. Especially in pure peer-to-peer, there's no central network device that's actually checking to make sure that the files you're receiving are actually accurate or virus-free. So you are taking a risk potentially in participating in certain peer-to-peer networks. As an aside, peer-to-peer networks have gotten a bad rap over time because often they are used to distribute files that are illicit or stolen. The technology itself is agnostic. There's nothing wrong with the peer-to-peer architecture, and there are plenty of businesses that use peer-to-peer for legitimate and legal purposes. So just because peer-to-peer has been used for illicit purposes does not mean there's something wrong with the architecture itself. It's just the purpose that is being employed by some users. In recent years, you've definitely heard a lot about cloud computing, and the term itself seems to be a little bit amorphous, just like the word cloud. Cloud computing is like your local area network, where your server often would store some of your files and have potentially some processing responsibilities. But instead of it being a server that is local to you and your business, the server is operated by a third party and you access it over the internet. So it's not really changing anything about the architecture we've been using for decades, except where that network resides. It's increasing the scale to take advantage of internet connectivity. Cloud computing has pursued a few different types of models. One of the ways we can use cloud computing is to support software as a service. In this model, all of the application components and any of the associated hardware and software are outsourced. Nothing is happening close to you. You're acting basically, again, as a thin client or a dummy terminal. Your device isn't doing any of the work. The work is happening far away from you. And the only difference between this and a host-based architecture is that we're taking advantage of the internet rather than a local area network. The other extreme would be infrastructure as a service, where we outsource all of the hardware, but we as a business are responsible for all of the other aspects of the network. So we're leasing all of the equipment, the servers, the air conditioning, the networking, but we are installing operating systems and applications, and we are managing all of the data, and we are managing all of the data manipulation and application processing. In the middle is platform as a service, where the application logic and the data are managed internally, But some of the other parts of a typical service are managed externally by another party. And an example of this might be something like Microsoft Azure. You can see as you move from the traditional thin client, client-server model to infrastructure as a service, to platform as a service, to software as a service, more and more responsibilities are being outsourced to a third party. And there are advantages and disadvantages to all of these models, and businesses tend to mix and match. In terms of how you choose the right architecture, there are lots of different considerations. One would be the infrastructure itself. How costly are the servers and the clients and the circuits? If these items are relatively inexpensive for your purposes, you might choose to own them. If they are particularly expensive, you might choose to lease them. We're also going to consider reliability. Some devices are highly reliable, but that reliability comes at a cost. If we need very, very reliable equipment, we might be looking at taking advantage of third-party equipment. We might consider development costs. It's typically much cheaper to develop on host-based architectures, where the software is only being hosted in one place. But of course, we know that those hardware costs can be quite high. We might be concerned with scalability. If we're a business where the needs that we have for computing capacity change dramatically over certain times of year or based upon certain product cycles, we might need scalability that would be difficult in an ownership situation, where we'd have to buy a bunch of equipment that we need for a short period of time, and then we'd have to not use that equipment or sell that equipment. Instead, we might choose to move to a cloud-based architecture where we can simply spin up virtual machines whenever necessary for our additional computing capacity, and then turn that capacity back off when it's no longer necessary. Now that we've talked about architecture, let's talk about some of the most common ways that applications take advantage of a network. The most common use for the network today is visiting the web. And this would be, at its simplest, accessing a web page using the Hypertext Transfer Protocol. So this is the application protocol that we use to get a web page from a web server to a specific computer client. The most basic HTTP request is just a simple text file. And you can see in this case that we are asking for a specific web page from a specific host, and then you can see some additional header information about where we're coming from and when we're requesting and what kind of software we're using to make the request. The response is also a simple text message that has some response status and has a response header and then has the actual contents that we're looking for, which are then formatted and presented on our screen as a web page. Another common application that accesses a network is email. There are lots of different ways that we can access email. The original mail servers used a mail transfer agent, and the original mail clients used some sort of mail user agent. The most common old school protocol for email was SMTP, which is still used today. Although it was originally only designed for text files, it has been modified with an additional protocol to handle graphics and attachments. Another common protocol for mail is Internet Message Access Protocol, and a third is Post Office Protocol. And many of these are again still used today for different types of email services. The beauty of the way our networking environment works is that different protocols can operate in the same network environment. So in this diagram, you can see that a computer client with an email client installed is sending an SMTP packet to an email server that is on their local area network. That email server is sending an SMTP packet to an email server in someone else's network. And that server is sending a different protocol email packet, either IMAP or POP, to a different client. So we're mixing and matching the different protocols for email from client to client without any issue. More likely than not, when you check your email, you are using a web browser, and this adds an additional layer. Your client isn't actually sending an email packet to a server. Instead, it's sending an HTTP request. When that HTTP request is received by the web server, it examines the contents and realizes that it's not really a web request. It's an email that you're sending. So it converts the information that you've sent to an SMTP packet and forwards it to the local email server. That email server will communicate with other email servers which might use different protocols. You can see the transition from one computer to another. You can see the transition from SMTP to POP in the bottom two servers. And you can see that the other client on the other end is also using a web browser. So the email is converted to an HTTP response and sent to that client as a web page, not as an email. This is a good example of an N-tier environment where we see multiple servers handling different types of requests, and those servers have been specifically designed for their tasks. A web server has different responsibilities and different needs compared to a mail server. I mentioned earlier that email was not necessarily designed originally to handle anything other than plain text. So an additional protocol had to be developed, which is multi-purpose internet mail extension. And this allows for you to take something that is non-text, convert it to ASCII characters, send it using a text-only protocol, and then decode that ASCII back to a picture or another digital file as necessary once it's received by the client. So an interesting workaround for a protocol that was never designed for the sorts of things we send via email today. There are lots of other application layer protocols that we use. For instance, we use a file transfer protocol for moving files from clients and servers. Old school users of the internet used to use something called Telnet for accessing a remote server using a text prompt. Many people still use IRC for chatting with other people, and in order to resolve URLs for web pages, we take advantage of the domain name system, which translates from the words you type in your browser to the IP addresses that the servers actually use on the internet. The primary implications for a manager when thinking about the application layer is to make sure that we are providing an environment where our application can thrive. We are designing our architecture so that things are going to work as smoothly as possible. We're designing for scalability where necessary. We're providing flexibility where necessary. And we're taking full advantage of all the various models so that we're keeping costs low. That's it for this chapter. Thanks so much for watching. See you next time.